So first thing we're going to look at is the CPU components. The control unit, or is sometimes referred to as the controller, directs the flow of data and instructions within the CPU. It controls the other components of the CPU. So our control unit is usually represented in Eduqas by a green oval. The registers are small storage locations found on the CPU. They're for temporary storing data or instructions. So in the diagrams, it's usually represented by the blue square. The ALU, which is the arithmetic logic unit, processes and manipulates data. It performs simple calculations on data stored in the registers and can compare data. So it can take two things out of register and can compare if they're alike. This is commonly shown as like a kind of winged symbol. And last is the internal memory, sometimes called the level 1 cache or cache memory. It's fast access temporary storage on the CPU. It's mainly used for frequently used data that needs to be accessed quickly and used again and again. This is normally represented by a pink square. So when it says CPU components, it's looking for the items that are actually on the CPU itself. It's not looking for things like hard drives or the memory or RAM or those sorts of devices or the BIOS chips. It's specifically anything built into the CPU chip. So looking at our specific CPU architecture, so this is going back to the components we talked about. The CPU architecture, this is one question in the CPU test that was a few parts quite often got wrong. So looking at this, part A, which is our winged V type shape, which is in red, is our ALU. Part C, which is represented by the green oval, is our control unit or controller, and B, the blue square, is our registers. So our ALU is the logic and maths operation device. The control unit focuses on the control of the data, the flow, and B is our registers, so it's our storage for information to be recalled to process by the CPU. So the important registers used by the CPU during the fetch, decode, execute cycle, there's three different ones. There's the program counter, or the PC, and this is a register that keeps track of the memory addresses of where the instruction is going to be executed next. So it will remember what it's done, so it'll be working through the program counter 1, 2, 3. Each of those is a memory box or a memory storage unit within the registers. So the program counter just keeps track of which one it's at. Then there's the memory address register, or the MAR. So the address in main memory that is currently being read or written. So the program counter keeps track. The memory address register is the one it's currently using. And finally, it's the current instruction register, or the CIR. So this is a temporary holding area for the instruction that has just been fetched from memory. So as it's processing through, the program counter is ticking over. It will pick up the next one and put it in the current instructions register, and that will be the temporary holding area for holding the current one just been fetched. The next part of the CPU, so it's our buses. So our buses are the data channels, or the channels that the current or information flows down. So our first bus sends data from one component to another. So this is our data bus. Our second one is the control bus. So this sends the control signals from the control unit to the other components of the computer. And finally, there's our address bus, which sends the address of where it's stored in memory. So it tells it which box in the registry that the address of the next thing to be used is. So moving on to the fetch, decode, execute cycle itself. This is a sequence of steps that the CPU performs again and again to process the running program. So the first step, number 1, is the program counter or the PC register is checked to find the address of the next instruction. Number 2, so the instruction is fetched from the address in RAM and transferred into the current instruction register. Number 3, once the instruction has been fetched, the program counter increases by 1. After that, we then move to 4. So the instruction is executed using the relevant components. For example, the ALU for adding two values together or subtracting two values apart. And then finally, at 5, the instruction is decoded by the control unit to understand what action has to be taken next. And after that, it then goes back to the program counter and starts the cycle all over again. So the next thing we look at is our cache memory. Cache memory is a type of storage that can be accessed by the CPU extremely quickly. It's because it's either close to or even within the CPU itself. Cache memory is used to store data that is frequently accessed and can be accessed faster than any other primary memory such as RAM. So this means that the cache memory in a computer system generally, the more cache memory, generally the better the performance will be. The downside of this is cache memory itself is really expensive. So most computers only really have a small amount of this cache memory. Next feature of the CPU is the clock speed. So the clock speed is the speed at which the processor operates. The faster the clock speed, the faster the computer is able to run through the fetch, decode, execute cycle. So therefore it can process more instructions. So we need to remember, the faster the clock speed, the more fetch, decode, execute cycles, therefore more instructions. So a speed of a processor is measured in gigahertz. So 1 tick per second would measure as 1 hertz. So a typical modern day CPU might run at a speed of 3.5 gigahertz. So it's the equivalent to 3.5 billion clock ticks. The number of cores. Core is the term used to describe the processing components within the CPU. So we've gone through the processing components, which are our control unit, the ALU, the registers, and the internal memory or the cache. So multiple core processors have many processing components within the same CPU. So they'll have multiple control units, multiple ALUs, multiple registers, multiple internal memory. So a single core processor executes one instruction at a time, whereas a multi-core processor can perform more than one operation simultaneously. So a dual core, two operations, quad core, 4 operations. So in general, a computer running many programs at the same time will run faster on a multi-core processor than on a single core processor. So the benefits we need to think about when we're mentioning how many cores is more cores mean more programs running at the same time at a faster rate. And finally, within our CPUs are our instruction sets. So CPUs can have different set of instructions so they can perform based on their function. So the two most common instruction sets are RISC and CISC. So with our RISC, with the complexity, RISC has fewer instructions than the CISC, therefore slower at carrying out complex instructions but quick for really basic tasks. Whereas our CISC can do more complex instructions and perform more complicated tasks. Looking at the cost, the RISC is generally cheaper to mass produce because less circuitry is required for the smaller instruction set. Whereas with CISC, CPUs are more expensive because they have more circuitry to operate. Moving on to the power side, RISC CPUs are designed to use less power and run without dedicated cooling systems, such as fans, water cooling, those kind of things. So these are more prominent in devices such as smartphones. With the CISC, because CISC requires more circuitry, it means that generally they get hotter and require fans or other cooling methods. So therefore CPUs are generally more commonly found in desktop computers or servers. Looking at clock speeds, RISC CPUs run at a lower clock speed than CISC, but they can perform simpler tasks much quicker than CISC, but are generally not used to carrying out complex instructions. On the opposite side, CISC CPUs run at higher clock speeds than RISC, and they can perform complex tasks more quickly than RISC. So examples of using the RISC are mobile phones, tablet devices, e-readers. So generally things that run off batteries, quite small devices, not big CPU type, not big computer things. Whereas the CISC processor is more focused on desktop computers, gaming consoles, and servers.